thank you very much for being here today. I'm very happy to be able to present you this idea I have for 7 months now, on which I'm working on, and which led me to this first paper called RisingBALLER. A player is a token, a match is a sentence, a first award, a foundational model for football players, data analytics. So I will start by showing you this kind of players cloud on which I put some random names like Rodri, Sergio Busquets, Bernardo Silva, Antoine Griezmann, Thiago Silva, Paulo Maldini, and so on. And what I wanted to highlight here is that by saying these names, you probably have a good knowledge about each of these players in terms of their individual ability as well as their collective ability. And you have such a good knowledge that you can even make some interesting clustering, like for example, Angel Di Maria and Trent Alexander-Arnold and Hakim Ziyech are 3 players with a very good passing quality. Zlatan and Romario, 2 retired players, but top striker with a lot of goals in their more than 500 goals in their career. Maldini and Thiago Silva, and so on. Now I will ask you a question. When it comes to data, how do we represent this player? So basically by using individual statistics and some advanced metrics like expected goals, expected assists, and so on. And by aggregating this statistic through a season or through a calendar years. And the thing is that there is a big limitation with this way of representing player in terms of data, because football is a collective sport, and when it comes to represent football players in terms of data, the main important aspect should be the collective aspect of the game. And that's probably a reason why a lot of coaches criticize statistics, because they are like, okay, football is a collective player. I have some key players in my team that maybe don't have like top statistic in terms of goals and assists, but who are very important in the team. If you take the example of Rodri at Man City, or Bernardo Silva, or Sergio Busquets at Barcelona, and so on. So, in the other hand, we are in this era of data-driven scouting and recruitment in football, in which a lot of clubs, more and more clubs, are using statistics to retrieve the best player to recruit. Because basically using data, querying a database is faster, it's cheaper, and above all, data is objective. So we need to find a way to represent football players in terms of data with features that explain their ability in the same way that we acquire our knowledge by watching them, and in all their individual and collective aspects. Now I will make an analogy with text model and with language model in general. We all know what are large language model. They are present everywhere today. But if we go back 6, 7, maybe 7 years before, the father of these models was BERT, for bidirectional encoding representation from transformers. And then we have Roberta. And these models basically encode all the semantic knowledge that a text could contain. And it's quite impressive to see the result that we can achieve with this text model. And the thing is that if we make some, let's say, basic analogy, we could expect to apply the same technology, the same architecture that work to learn this kind of foundational semantic representation to encode words. We can apply the same architecture to encode football player. Of course, football is not text, but football is a language itself. And this language, we can see football matches as the sentences of this language, and the players are the words. And that motivates what I'm going to present now. So I will start by presenting you how I apply the architecture that work and lead to this impressive result for text. I will present it first. So how I apply this architecture to model football player, how I train the model, and then the application of this kind of architecture. Basically by using this representation that the model will learn, what we can achieve with this representation. And then finally, I will make a recap of the presentation, present the limitation of the works, and some direction for future explorations. So let's start with the model architecture. So welcome RisingBALLER. So what is RisingBALLER? RisingBALLER is a transformer-based model for learning foundational high-level contextual feature to represent football players. So basically, this architecture model football matches as a set of players with a well-defined structure. So each player will be represented with a unique ID. So each player in the input of the architecture will be represented with 4 things. So each player have a unique ID. So basically, you have a vocabulary, a defined vocabulary of players in all the data set that will help to train the model. We have a unique ID per team as well, a unique ID per position. So basically, in the StatBomb data set, you have 25 unique positions on the pitch, and each player will be represented with a unique ID based on the position he occupied on the pitch. And then you have some raw statistics that come from event data with any processing step, and you will use them as a kind of temporal encoding to model, let's say, the current form of the player at the moment of the matches. So you probably understand it. So this architecture encodes directly football matches. So quickly, how the model encodes the players in the inputs. So it will make a weighting average with all other players in the matches, and the weights will be computed by making a scalar dot product between the player and all other players, followed by a softmax operation to have a probability vector. And it will do that for all the players in the input sequence, and will output all the same players with contextualized feature for each player. This operation is attention mechanism, and it's the main operation inside a transformer network. And now I will present how do you train this kind of architecture. So basically, it's through something that can look very naive as task, but it's working. And this task is masked player prediction. So basically, you have the set of players, well structured, you mask some players, and then you train the model to predict the players that are masked. And here, basically, for each player that are masked, the model will predict one player between all the vocabulary of the players available in the data sets. So for this work, I use all matches of the top 5 European league for the 2015-2016 season. So it's, let's say, 1,800 matches, 2,000 and 600 unique players, and 98 teams. So these are the results of the masked players prediction pre-training. So the model is trained with cross-entropy loss. And here you will see that the two models, so I trained two models. So one model with 64 dimension as embedding size, and one model with 128 dimension. And the two models are able to reach almost 80% of accuracy. But what's more interesting is when we look at the top 3 accuracy. So in more than 95% of cases, the model are able to find the right masked player between his top 3 prediction. And that's very nice because that confirms the choice of this architecture to model football players. This architecture that work well for text. So now that we design this architecture and we define this masked player prediction task. So how we can use this embedding? And now I will show two interesting applications of the embeddings that the model learns. So first, I have a question for you, which is what make a good player's embeddings? So basically, do players in the same team should have similar embeddings, or do players with similar profile should have similar embeddings? And what's interesting here is that RisingBALLER show the ability to learn both aspects. So first, I remark that train the model with team affiliation embeddings. So the team ID that I add in the input representation of each players before the attention mechanism. So train the model with this team affiliation embeddings lead to a model that learns similar embeddings for players in the same team. And this allows for estimating a team cohesion metric. And train the model without these team affiliation embeddings tend to learn similar embeddings for players with similar profile. And that's enabled direct application for data-driven recruitment through similar player retrieval. So first, I will show you this example of a dissimilarity heat map between Barcelona and Real Madrid using the embeddings of the model trained with the team affiliation ID. So you can see here that there is clear blocks within each team, which show that the model tend to learn similar embeddings for players in the same team. And what is good with this is that using these embeddings, so we can estimate a kind of team cohesion factor. So basically, it's the average of total similarity across all players in the same team. Because you have a model that are good to learn similar embeddings for players in the same team. So by computing this metric and compare this metric across different teams, we can retrieve which team have the highest cohesion factor. And this is the top 10 team in the dataset that have the highest cohesion factor. So you can find Leicester City, the surprising champion, England Premier League champion during that season, that 15-16 season. You can find the Real Madrid, the surprising European champion during that season as well. You can find team like Stade Malade de Caen, which finished at the 7th position in Ligue 1 that season. But you can also find team like Gazélec Ajaccio, who was relegated in Ligue 2 that season. So now that we saw this result with the max player prediction with the team affiliation ID and the tendency of the model to learn similar embedding for playing the same teams, so I applied the team affiliation embedding, so I remove it in the input representation, and I return the same network in the same condition. And now it appears that it's more difficult for the model to find the mass players, even if the model with 128 embedding dimension, so with more capacity to learn more features, could still reach 88% accuracy in top 3. And that's very interesting because now that the model don't have this information, it's obliged to learn some pattern based on position, based on, let's say, similar statistics, similar form of player during the match, or based on the frequency of the matchup between players and some opponents. And it's still working. So that's very interesting. And if we look at the same heat map, the same dissimilarity heat map like before between Barcelona and Real Madrid, now we'll see that the similarity between players in the same team are less pronounced, and the model learns similar embeddings for players with similar profile like Benzema and Suarez, Neymar and Ronaldo, Varane and Piqué, even if they are not in the same team. And that's really interesting because now that demonstrates the ability of the model to learn similar embedding from players with similar profiles, something that have direct application in data-driven player retrieval and recruitment. So now I will show you a quick demo. So this is a players retrieval application I built based on this idea of removing the team affiliation embedding, and the model behind the application, which is online. You can play with it. So it's trained on all available matches on the Statsbomb open data. Okay, so here we are on the retrieval application built on the RisingBALLER models, trained on all matches available on Statsbomb open data. So you have some statistics about the match that help to train the model. And what's interesting is to see that, I mean, I use matches from 20 football seasons, so you don't have any restriction about the football season. So you don't need any statistic aggregation or that kind of thing. All you need is just matches. You define your player's vocabulary, and then you train the model, and it will learn anything. And let's make an example of retrieval. So if I choose, for example, let's choose a playmaker like Mesut Ozil, for example. I will ask for, I don't know, let's say, okay, 20, more than 20 players to retrieve. I will increase the minimum matches of the player to retrieve, just to have some reliable result and to avoid the outliers. And I will ask for players in Serie A, in Liga, in Bundesliga, because I know that there is a lot of matches of Ozil in Premier League and in La Liga. Maybe I will add Premier League just to see if the model could retrieve similar players. So if you look at the output, so have Oscar. So this is very interesting. If you remember who is Oscar and how he play. Alexis Sanchez, so Ozil teammate at Arsenal. Olivier Giroud, which is a pure striker. That's quite interesting. But you have player like Gifli Sigurdsson, which is very interesting in terms of profile, similar to Ozil. Bojan Kirkic, Mathieu Flamini, so these are Ozil teammates. Chiku Kouyaté, very interesting as well. Sex Fabregas, Adam Lallana, Philippe Coutinho. Here you have Per Mertesacker, which is a defender. Maybe probably because he played a lot of matches with Ozil at Arsenal. This is probably because of the bias also in the data set. Sadio Mane, Ibrahim Afellay, Cristiano, Dele Alli. So it's very interesting to see the diversity in the retrieval. So the model could retrieve pure players that are similar to Ozil in terms of pure profile, as well as players that are compatible with Ozil, like Olivier Giroud, for example, or Cristiano Ronaldo. So that's very interesting. And if you remember my introduction, the idea is to train a model that could learn foundational features to represent all aspects of a football player, and that could directly serve as a player retrieval as a player retrieval tools. And it's very interesting to see the result of this kind of retrieval. And the application is online. You can test it, and feel free to share some feedback about the quality of the retrieval using this link. So that is. So now let's recap what we did so far, and let's present some limitation of the architecture and some future direction for some future work direction.
Now, as a recap of the presentation, I think if there's one thing to remember is that what I present is an architecture to learn foundational features to represent football players. In the same way, we acquire knowledge about these players by watching them match after match. And what's really interesting here and what's original is that to achieve this result, all we need is just lineups data and some match level raw statistics, and the model is designed to learn any feature relevant to represent the players.
Of course, the work and the model have some limitations. So all the trainings were done on a small and unbalanced data set. So we need to leverage a larger data set, because also we know that transformers are the kind of network that perform well in large scale. We need to find some direct way to interpret the feature that the model learns, even if we show that through some similarity query, we can see that the model is learning similar embedding for players with similar profile. And we also need to find more rigorous method to assess the team cohesion factor and the player's retrieval. Basically, for the team cohesion factor, we can evaluate his correlation with some well-known team's performance metric. And for the players retrieval, something that could be interesting is to ask for some expert knowledge to evaluate the quality of the retrieval. Possible future exploration. So there is two applications that I didn't present here due to the time restriction. So an interesting downstream task. So basically using the embeddings that the model learned for player to predict some next match statistics, and also make some analysis on the positional embeddings that the model learns. So these are described on the paper for the one who are interested in it. It's some interesting application of the model as well. And in terms of pure feature work, so we definitely need to scale the model, because we have a good advantage. We have a massive literature on how to scale transformer and how transformer perform well in large scale. So we could take advantage of that available literature to study, in this case of players modeling. An interesting ablation study could be to assess the impact of the raw statistics. Maybe by leveraging massive data, we'll find that only lineup data with some position ID is all we need at the end. And also the attention matrices in the network could open a new way to model players interaction. So unfortunately, I wasn't able to be there due to a visa issue. But some word about myself. So I'm Achraff Adjileye. I hold a master's degree in applied mathematics. I have background in natural language processing, in computer vision, and in classical machine learning. I'm a Chelsea Football Club supporter since my young age, and I'm an agile prototyper, because what I like above all is to find solution to problem, to quickly design solution that will have direct impact. So thank you very much. You can contact me by my email address or on LinkedIn. Feel free to reach out if you have any question or and I will be more than happy to respond. So thank you very much.